Hello and welcome to our next portion of our polar coordinate unit. We are converting, we've covered plotting coordinate points or polar coordinates. We've also worked with converting from polar to rectangular and rectangular to polar, and now we are taking it up a notch. We are now converting rectangular equations into polar equations. So we're going to see a whole bunch of graphs, and this is going to be really interesting in how a graph will look in the XY plane or the coordinate plane versus the polar plane. So before we start, we actually need a whole bunch of equations. We need to recall all of these original equations that we worked with in converting polar coordinates to rectangular and vice versa. Okay, so first set we used to convert from polar to a rectangular coordinate. And here, r squared is equal to x squared plus y squared. We are converting from rectangular to polar. So if we remember, rectangular coordinates are always x, y. Polar coordinates are always r comma theta. Now, we also need 4 new sets of equations. Well, technically 5. It's a recall for cotangent, but it's not important right now. We should be able to recall, well, here's the nice part. If we wanted cosine by itself, we could actually derive all of these equations from these two. So, for instance, if we wanted cosine theta by itself, like we do in this red equation, all we need to do is get rid of r. We divide both sides by r, and we should get, I'm going to do that in pink so you don't copy that down, divide by r, r's cancel out, and you end up getting the new equation, x divided by r. Okay? Same thing happens for this equation. If we wanted sine by itself, we would divide by r. So we divide by r, and then we end up getting sine of theta is equal to y over r. Which brings up cosecant and secant theta. Well, secant theta, we know, is just the reciprocal to cosine. So we could actually take this ratio and actually flip it. So we take r over x instead of x over r, and we have secant theta. Similarly, sine theta and cosecant are reciprocals, so we could take the reciprocal to y over r, which is r over y, and we have our fourth equation. Now, I did mention that we could work with cotangent as well. This is kind of a bonus if we need it. Cotangent theta is equal to x over y, in case we forgot. So here are our equations that we are probably going to use to convert equations from rectangular to polar. Our first one, and excuse this, we already have some here. We actually need to take x and y, and we're going to actually take these versions of it and substitute these in. So x, if you notice, is r cosine theta. We're going to substitute this in for x. Same thing here. We're going to take the y, and we're going to substitute in r sine theta. So our new equation is going to take these original equations and substitute a whole bunch of information in. Instead, though, we're not going to have 2x. We're going to have 2 times r cosine theta. Sorry. R, and put them in parentheses, cosine theta. And then I'm going to plug in, so this is our x turned into this, r cosine theta. Y, so we're going to continue the plus y. It's technically a 1. If you want to put a 1 here, you can. You don't have to. Times y, r times sine theta. Because that's what y is equal to. We substituted it in. And set this equal to 1. And whenever we're solving with these problems, we want to isolate r. So after you substitute this in, our whole goal will be to isolate r. Okay, that's how we typically write polar equations when r is by itself, kind of like how y is by itself. Y is equal to mx plus b, right? We want the y by itself. In this particular case, we want r by itself. It's a little easier to understand if you have r by itself. So to get r by itself, I'm going to drop these parentheses now because this is all multiplication. I'm going to get rid of that 1, 2 because we don't need it. If you notice here, we have an r in both terms. We could actually GCF that out. GCF of r. So that means we put the r on the outside of the group. Have everything else on the inside. 2 still being multiplied with cosine theta plus r is now gone here. So now we're just left with sine theta is equal to 1. So that's the whole idea. We want r by itself. We needed to get the r. There are 2 r's here to begin with, separated with a plus sign, so we actually needed to factor it out. Once this is factored out, we can now divide out this entire group. Divide both sides by 2 cosine theta plus sine theta. Because this is multiplication, you can do this. Anything you do to one side, you have to do to the other. 2 cosine theta plus sine theta is being divided out on the right side. These cancel out on the left, and now you have r by itself. R is then equal to 1 over 2 cosine theta plus sine theta. Okay? And this is your equation converted from rectangular to polar. Now, if you're curious to see how this looks on a graph, I put on here a whole bunch of equations that we're going to see. And if you notice, this first equation here is what 2x plus y is equal to 1 looks like in a normal graph. If I change this from polar to rectangular, you'll see what I mean. That's what it would look like. The polar coordinate system is just an overlay onto the xy plane, except you don't have the boxes anymore. And if you convert this, which we have here in the second equation, it is the exact same graph. So if you went from blue to green, or red to blue, because the red is the rectangular equation, the blue is the polar equation, they should be completely identical when I jump from back and forth. So that is perfect. Okay, so next one, let's convert this next equation. We're going to take that y, we're going to substitute in r sine theta. So this is going to be r times sine theta minus 2, x will be r times cosine theta is equal to 8. Once again, we have r in both terms, so we could factor it out. That's our GCF, r, and we factor out, we have sine theta minus 2 cosine theta inside the parentheses is equal to 8. Our whole goal is to isolate r, so we divide out the sine theta minus, the r should be gone. There should be a 2. So 2 cosine theta. So divide by sine theta minus 2 cosine theta. R is now equal to 8 divided by sine theta minus 2 cosine theta. All right, and this is what it should look like in our graph. Y minus 2x is equal to 8. It's that green line. If we did this correctly, r is equal to 8 over sine theta minus 2 cosine theta, and we see that they overlap each other. And that is perfect. Green to purple. So nothing is changing between this besides how the equation looks. Now what happens though when we have an x is equal to negative 3? Hopefully you're able to remember that this is just a vertical line. Okay, so here it is in the black, vertical line. Well, the moment we convert x, so we know x is equal to r cosine theta, we have our two variables there. R times cosine theta is equal to negative 3. All we have to do this time is divide out cosine theta, which is kind of nice. Cosine thetas will cancel, and r is equal to negative 3 all over cosine theta. So if we did this right, our graph will look like a vertical line in the polar coordinate plane, which it is. So you can see that between these two graphs. From black to red, they are the same graph. All right, and here's the last one. This one's the weird one, and I put special case above this because it's kind of like a vertical line, a horizontal line, but for polar coordinates. Notice in this equation, we only had one variable, x, we were missing the y. The same thing's gonna happen here, but instead, we're gonna lose an r. So in this particular case, we're going to set them equal to each other. We know y is equal to r sine theta, and then x is equal to r cosine theta. Okay, so this is the weird part. And you could do this actually one of two ways. I probably should have done this first. I probably would divide out the x so that the x and y's are on one side. X's will cancel out, and you get 1 on that right side. So you get y over x is equal to 1. When you substitute in, you end up getting r sine theta over r cosine theta is equal to 1. So r's in the numerator and denominator will cancel out, and you get sine theta is equal to cosine theta. Hopefully you remember this. Cosine over cosine is actually equal to tangent theta. And tangent theta is equal to 1 has two solutions, typically. Well, a lot of solutions. You want to get theta by itself in this particular case. So at this particular case, you want to solve for theta since, oh, let me do that in bubbles. Since the r canceled out, you want to solve for theta this time. Inverse tangent both sides. 1 goes inside the group. Theta will then be equal to 45 degrees if you do this in your calculator. But 45 degrees doesn't show up as a line in the coordinate plane. So if you scroll down here, it's technically pi over 2. And if I graph this, actually let me erase these first. We don't need those two. If you graph this, it is a line from y is equal to x is a diagonal line from bottom left to top right. Pi over 2 does land in that, should land in that spot right here. You can't see it, between pi over 3 and pi over 6. But it does not show up when we just graph theta is equal to pi over 2. This is where we need to be able to recall, okay, theta at 45 degrees for tangent, when tangent is equal to 1 is 45 degrees, it is also technically, or 225 degrees, because if you add 180 to this, plus 180 degrees, you are landing in the bottom left quadrant, quadrant 3, which is 5 pi over 4. And the moment you have 2 points, you can make any graph, right? If you recall, anytime you want to graph something, a linear equation anyway, you need 2 points to graph. Whether it's these 2 points, you connect them, use your slope to connect them. In this particular case, we want pi over 2, which is 45 degrees, and 225 degrees, pi over 4, and 5 pi over 4. The moment you have both of these points, so you could put pi over 4 or 5 pi over 4. The moment you have both of these points, you could connect these, and you will get that exact same line as y is equal to x. It is the same line, okay? So we are now converting to from two polar equations, from rectangular to polar equations. These are the equations you need, and we need to do make sure we do a good job substituting in. If you do have any questions, please let me know, and I'll see you in the next one. Bye.